Welcome back to The Explainer. Today, we're tackling something absolutely fascinating that sits right at the intersection of computer science, engineering, and art. We're going to look at exactly how we make digital characters and physical robots move naturally in 3D space. It's something we see literally every day, from blockbuster animated movies to automated factory floors. But the mechanics behind it, they are absolutely mind-blowing. Picture your favorite video game character for a second. When you run them up a rocky, uneven hill or down a jagged flight of stairs, how does that character intuitively place its foot perfectly on a rock without just floating in midair or clipping right through the geometry? I mean, it looks like magic, but it's actually a massive, real-time mathematical puzzle. And today, we are going to crack that puzzle wide open.
So, here's our roadmap for today. First, we'll look at forward kinematics, then the Dennevit-Hartenberg convention, move into inverse kinematics, and finally, solving the inverse problem.
Okay, before we get into the weeds, let's just lock this core concept into our mental map. Forward kinematics is straightforward. You input the joint angles, and bam, you get the end position. Inverse kinematics, that's the reverse. You start with a target position, and you somehow have to calculate all the joint angles to get there. Just keep that contrast in the back of your mind.
All right, let's dive into this. Section 1, Forward Kinematics, moving forward. To really get this, we've got to understand the physical or digital skeleton we're working with. It's called a kinematic chain. Honestly, just think of it exactly like your own arm. It's a series of rigid segments, like your bicep and forearm, connected by joints, like your shoulder, elbow, and wrist. Whether we're talking about a massive robotic arm building cars on an assembly line or a 3D model of a dragon, it all starts with this chain.
Now, at the very end of that chain is something called the end effector. That's the tip or the final link. Going back to our arm metaphor, it's your hand. On an industrial robot, maybe it's a mechanical gripper or a welding torch. In a video game, it could be a character's foot reaching for the ground. Basically, the end effector is the part of the chain doing the actual work or interacting with a target.
So, what actually is forward kinematics? Well, it's simply the process of figuring out exactly where that end effector is going to end up based purely on the angles of the joints behind it. If I tell a robot, hey, rotate your shoulder 45 degrees, bend your elbow 90, and twist your wrist 10 degrees, I can use forward kinematics to mathematically calculate the exact 3D coordinate where that hand will stop. It's super predictable. You know the angles, you find the position.
Which brings us to Section 2, the Dennevit-Hartenberg convention, the blueprint.
But how do engineers and programmers actually standardize and write the math for all these wild 3D movements? We have to take a quick trip back to 1955. Jacques Dennevit and Richard Hardenberg introduced a convention that literally changed the game for spatial linkages. Before they came along, tracking the relative movement of all these twisting, turning joints was just incredibly chaotic. They created a standardized blueprint, a universal math language really, that lets us attach coordinate reference frames to each specific link in a robotic chain.
And what's so cool here is how they distilled the infinite complexities of 3D movement down to just 4 distinct parameters. You've got d for the offset along the z-axis, theta for the angle around that axis, r or a for the length of the link, and alpha for the twist angle between the axes. These 4 parameters act like a universal translator. Just by plugging in these 4 numbers, you completely define the physical dimensions and screw displacement from one joint to the absolute next.
So when you take those 4 DH parameters for a joint, you can plug them into a transformation matrix. And hey, don't worry about the heavy calculus here. Just think of a matrix as a set of mathematical instructions. If you chain these matrices together, multiplying the matrix for the shoulder by the matrix for the elbow by the wrist, you get one master transformation. It perfectly characterizes the location and orientation of the end effector. It's essentially a foolproof mathematical blueprint for the robot's entire pose.
All right, here comes the plot twist. Section 3, Inverse Kinematics, Reversing Direction.
In video games and modern robotics, we almost never have the luxury of just inputting joint angles. Think about it. When you point and click your mouse to tell a game character to pick up a sword, you aren't typing in shoulder and elbow angles, right? You're just giving it a target position. So, here's the crucial point. You know the target, but your computer has to rapidly calculate in reverse how all the joints must bend to get the hand exactly there. Without this reverse math, characters would just float above the ground, and factory robots couldn't dynamically grab moving parts on an assembly line.
And this is exactly why IK operations are computationally much more complex than forward kinematics. Why? Because while forward kinematics only has one possible answer, inverse kinematics can have infinite answers. Think about your own arm again. If you hold your hand steady on a doorknob, that's the target, you can still wave your elbow up and down wildly. There are multiple configurations to reach the exact same goal, and figuring out the most natural, efficient one, yeah, that's a massive computational headache.
So how do we fix it? Section 4. Solving the inverse problem. Cracking the code.
How do engineers actually solve this massive reverse engineering puzzle? Well, our first tool is the analytical solution. This is a closed-form direct math equation that spits out the exact joint angles. It's incredibly fast and highly precise. But there's a huge catch. It only works on very specific, standard physical geometries. Take, for instance, industrial robots designed with exactly 6 degrees of freedom where the last 3 rotational joints intersect, which is known as a spherical wrist. If your robot or video game monster has a weird number of joints, the analytical solution completely falls apart.
When the geometry gets too complex, we turn to numerical methods, specifically the Jacobian inverse technique. Now, I know the Jacobian matrix involves mapping velocities and taking partial derivatives using Taylor series expansions, which sounds totally terrifying. But conceptually, it's really just a simple loop of guessing and checking. The system estimates a movement, calculates how far off the hand is from the target, and then uses the Jacobian matrix to figure out a tiny adjustment to the joint angles. It repeats this loop incredibly fast until the error drops to 0 and the hand hits the target.
But sometimes, even the Jacobian is too heavy, especially in a video game where you've got to render 60 frames a second. That's where heuristic methods come in. These rely on simpler, faster iterative rules rather than heavy calculus. We're talking about methods like cyclic coordinate descent, or CCD, and fabric. They adjust one joint at a time, moving up and down the chain iteratively until the end effector reaches the target. They're fast, they have a really low computational cost, and they're extremely flexible. Basically, they're the absolute favorites of the computer animation and gaming industries.
So when engineers are building these systems, they constantly face a delicate trade-off between speed and flexibility. If you have a factory robot doing the exact same precise weld 1,000 times a day, you build it with a spherical wrist and use analytical solutions for blazing speed. If you have an unpredictable robotic spider walking over rubble, you might use numerical Jacobian math for the accuracy. And if you have a superhero in a video game climbing a dynamically collapsing building, you're definitely using heuristic methods like fabric to keep the game running smoothly.
It's honestly amazing how much math goes into simply putting one foot in front of the other in a digital space. But it leaves us with a really exciting question for the future. As neural networks and machine learning models learn to mimic physics based entirely on massive datasets of video capture, are we eventually going to bypass these traditional DH parameters and Jacobian matrices entirely? Will robots and digital characters just learn to reach and step organically, rather than being solved like a complex equation? It's a thrilling frontier to think about. Thanks for joining me on this deep dive into the mechanics of movement, and keep exploring.